Hello, my name is Carly Franklin, and this is my submission for Lab 5, Magnetic Braking with Faraday's Law. As an introduction, the goal of this lab is to investigate the fields created by magnetic induction due to a falling bar magnet within a copper tube. And then the next step of this lab is to model the magnet's interactions with the tube computationally and then compare our computational data to the observed data. The fundamental principles that this lab relies on are Lenz's law, the Biot-Savart law, and as Newton's second law for balancing gravity and mass and acceleration. I set up my experiment using a bar magnet and a copper tube provided to me, and the system includes the bar magnet, and the surroundings are everything else, including the copper tube. My initial conditions are shown in the slide and will be shown as well in my GlowScript code. And then to conduct the experiment, I first recorded the time it took for my bar magnet to fall the length of the copper tube, and then the time it took for the bar magnet to travel through the length of the copper tube. In conclusion, my computational model had a significantly larger value that was calculated for the dipole moment and approximately the same time to fall through the tube. And that dipole moment is in comparison to my dipole moment from Lab 4 for a magnetic, or for the bar magnet. And here are my calculations from Lab 4. That is my previous magnitude of my dipole moment. And as we will see later, it is much smaller than the one I got from this lab. So here is my computational model shown. We use GlowScript for this lab. You can see my code basically treats each slice like a ring, and that's where you're kind of getting superposition. But also, it uses principles of Lenz's law because as the bar magnet is traveling through the tube, there are forces that are counteracting it. And then you can see the correct magnitude for mu that I got from my GlowScript code. And this is the last of my code where I calculated the flux through the copper tube. And then the very last step is what allows for all of those to be added together. And here is my comparison between my two graphs. The one shown in red is from my previously calculated dipole moment. So as you can see, it is it's definitely not correct for this model, but on the left you can see my new computational magnetic dipole moment, which looks much more like it's supposed to. And I got 12.85 seconds in reality, so I matched that up to my computation. And that brings us into the discussion. So my experimental, not model, I didn't have a model. My experiment and my computational model have an identical duration of time taken to travel through the full length of the copper tube. And then I just adjusted my mu mag until it was the correct value to get 12.85 seconds. And from Lab 4, my magnitude of the magnetic dipole moment was not aligned with the one I found in Lab 5. And this is mostly because the models are just approximations from their specific contexts. And neither are 100% accurate, but they both represent their circumstances. Lab 4 was by using a magnetometer, and Lab 5 was by calculating the time it took to travel through a copper tube. And now we have further discussion. What if the resistivity of the conductor was reduced? And the conductor being the copper tube, and if that had a lower resistivity, then the current would be allowed to be larger. And I put the equation in my response as well. An increase in current would lead to a stronger magnetic field opposing the magnet's motion, and this is confirmed by Lenz's law and Newton's second law. So it would take longer for the falling magnet to travel through the tube. And what if there were holes, or what if there were just interruptions into the tube? Well, this would make my model now incorrect because the model is assuming that each component of my tube is a full ring with no interruptions, as I showed in my closed script code earlier. So cutting holes would create incomplete sections that no longer have current flowing through them due to the interruption. And so the estimation of my current in my closed script would not be accurate or close to the real value of the current. And that's the end. Thank you for listening.